All right, everybody, 24.2 notes. So here we go, 24.2. We talked about harmonic motion with 24.1 and really just kind of figuring out what that harmonic motion and repeated motion, what waves are, right? We talked about cycles and wavelength, amplitude, damping, all those things, right? And today we continue on with that. It's a lot of vocab again. And this section 24.2, we kind of go into more specific details about what those waves are. And then we talk about what happens when waves collide with one another or collide with other things, okay? When there's some sort of interference. So properties, here we go. What is a wave? A wave's an oscillation that travels from one place to another, and we've already seen that one, okay? Oscillation that travels from one place to another. The tough word there is oscillation, and I always like to think of that. It always reminds me of a fan that is oscillating. An oscillating fan, when you set a fan to oscillate, it goes back and forth, right? So that back and forth motion, that's an oscillation or a wave. If we're talking about waves in water, which we see, well, that's easy for us because we see those waves. That back and forth motion isn't back and forth or in a circle, but it's up and down, that water moving up and down. So if you poke a floating ball, it oscillates up and down. The oscillation spreads outward from where it started. A wave, let's see, already did that one. So you can just kind of see this picture just kind of shows you those ripples. This just kind of illustrates what is happening there. So when that ball goes in, that ball is taking up water. So you drop that ball, you drop a rock into water, and it's taking up area, or it's taking up a volume of that water. And basically the water that was there needed to be pushed to the side, right? So you can see how it like elevates that water right in here. And now that part kind of propagates out. It disperses outward, and we get this wave. So that's kind of how waves in water are actually made. Now we get into some terms. Frequency, we already learned about. Frequency means how often, but I don't like that term. Just how often doesn't really tell me about what that word means in science. Okay, frequency in general means how often. The frequency of my lawn mowing would be maybe once or twice a week, depending on the week, things like that, right? So that would be frequency is generally is how often, but frequency in science, we're talking the rate at which every point on a wave moves up and down. So how many cycles per second is the term we used with 24.1? How many cycles per second? The rate at which those cycles occur. That's what frequency would be. If we're talking about water, the rate at which it goes down and back up. Okay? We measure frequency in hertz, and you can see the waves here with water starting up, going down and back up and down and back up and down, right? When it goes one of those cycles, starting at the top, going down and back up, that would be one cycle. And how many of those cycles happen each second is our frequency. Waves are moving series of high points and low points, right? So when we look at that wave, we see, okay, here's a wave where the water is high, and here's the point on the wave where the water is low. The crest is the peak, okay? That's where it's the highest, and the trough would be the lowest, okay? So crest is the highest point, the trough is the lowest point of a wave. So two vocab terms again. I'm gonna get you the Quizlet for this as well, so you'll be able to study these vocab terms using that Quizlet, which is kind of nice. Next up, we have amplitude. We already talked about amplitude was that distance away from equilibrium, right? And now if we're talking about waves in water, specifically, we're going to be referring to the height that wave rises above sea level. So that equilibrium point in water is surface level. So that maximum height above or below, that would be our amplitude. Okay? This picture shows that, no problem. All right, now a term that we hadn't gotten yet is wavelength. Just like the term sounds, wavelength is the distance from any point on a wave to the same point on the next cycle. Okay, so a wavelength, the distance of one wave, or the distance of one cycle. Okay, between the crest and the next crest, or the trough and the next trough, wherever it starts to repeat itself. Okay, you guys looked at pendulums. We talked about pendulums. with the 24.1 notes, and you did an activity with pendulums. And that wavelength for a pendulum would be the distance it travels when it went from that point up here, okay, from the amplitude, high amplitude on this side to the other side and back. Okay, if we were to measure that distance, that could be the wavelength. The speed of waves, the speed of a water wave is how fast the wave spreads. So when we look at wave speed, I don't want you to confuse wave speed with frequency. Okay? The wave speed is not how fast the water moves up and down. That's frequency. Okay? Wave speed is how fast that wave, the energy, moves across. So for an example, if I throw a ball in a pool, okay, and that eventually that wave that is created, those ripples that are created, will get to the edge of the pool, right? How fast they get there is considered our wave speed. So kind of like speed, like running speed or driving speed, where it's your distance divided by time. Wave speed is basically the same thing. Now we take a little roundabout way of getting there, and we use the wave terminology instead of just saying distance divided by time. But in a nutshell, it really is, and we'll show you that here in a second too. So wave speed is the distance traveled divided by the time it takes. So we can take distance divided by time is speed, right? Now, if we're talking about waves, we have some terms for those for distance and for time. Our term for distance would be wavelength. So we can take one wavelength divided by one period, right? The period is the time it takes for one cycle, the time it takes for the water to go down and back up. Okay, that could be the period. Now, what we actually use, though, instead of using period, we use the frequency. Frequency, remember, is the opposite of the period. It is, instead of how long it takes to complete one wave, it is how many waves are completed per second, measured in hertz, right? So here is the math behind that. We have the speed is equal to distance divided by time, right? We know that. We learned that back in chapter 4. So when we're talking about waves, we change that to wavelength is our distance divided by period, which is our time. Distance divided by time, wavelength divided by period. Okay. Now, we also learned in 24.1 that frequency is equal to 1 divided by the period. So I could rearrange this equation of wavelength divided by period. That's the same as 1 over the period times the wavelength. That's how the math works out to be. And I can substitute that 1 over the period for frequency. So this here is the equation we will use. Okay, so wave speed is going to equal frequency times wavelength. And I'll tell you right now, in your section review questions, you will need to answer one of these questions. You will need to use this equation, frequency times wavelength equals speed. That is something that you will be tested on. Here is the equation for this. Wave speed, velocity right here. There's my F for frequency. And this little symbol here, lambda, is what we use for wavelength. Okay, so wave speed is equal to frequency times wavelength. Frequency is measured in hertz, and our wavelength should be measured in meters. And it could be centimeters or something like that. That would be okay. But our time will be seconds. So our units will be wavelength in whatever unit divided by per second. In this case, meters per second. And I think the example that we have you do in your section review is also including meters. I think we try to stick to meters and seconds for you, okay? Now, that's enough about the different properties again. So we've gone through wavelength, wave speed, frequency, all of those things. And now what happens when waves interact with other things? Like I gave you an example of throwing a ball into a pool. Eventually that wave is going to hit a boundary. It's going to hit the edge of the pool, right? Well, what happens to that wave? Okay, that's what these are. So when a wave encounters a surface, we have one of 4 interactions that can occur. The first, reflection, refraction, diffraction, or absorption. So reflection, just like it sounds, that wave hits that wall and it bounces off. Sound is an example of a wave. It's not like a wave in water. It's a different type of wave. But anyway, the sound might bounce off of a wall and come back at a different angle, right? So that would be a reflection. Okay, the wave bounces and goes in a new direction after it hits that boundary. Refraction is another example. Okay, here's an example of a light wave passing through a lens. Okay, the wave bends as it passes through this object, and we change the way that wave is coming in, or change the way it leaves, I guess. So we're changing the shape of that wave after it passes through an object, and that's what like we all have a lens in our eye that does this. It takes the image that comes in and it bends it to focus it on the back of our eyes. My lenses in my eyes are not as good. They're not focused in the right spot. So I have to have corrective lenses, glasses or contacts that actually bend the light before it gets to my eyes that will then bend it again. So they're just correcting that that refraction for me. Okay. And then another one is diffraction. You guys have seen this all the time with light as well. Light's kind of a good example because you see light, right? So you've seen this if you have a room that's completely dark and you crack the door open, you see that the light that enters will spread out and not just stay in one single line, right? It will spread out and cover more area. Oftentimes it'll be, like at a triangle towards that wall until it runs out, until it hits something else, right? But that would be diffraction. It bends around a corner. And then the last one is absorption. The wave can sometimes just be absorbed and disappear. And that would be like in a music room or band room, things like that. They might have things on the wall to absorb or reflect or refract those sound waves. So they might have some padding on the wall to absorb those sound waves so that it is not bouncing around the room and echoing like crazy, right? So that would be absorption. Well, light waves can just enter something and not be able to leave. The energy of that wave is absorbed by whatever object it ran into. Again, those are 4 things that can happen whenever you run into something else, okay? Whenever that wave encounters an object. Hey, this is an example. This one's actually pretty cool. We would do this in a lab where we send what's happening here is that we're sending a plane wave, and all this is illustrating is diffraction. We're sending a plane wave at this boundary here. Okay, so this would be a wall, but this wall happens to have a little tiny hole right there. So as that plane wave hits that boundary, you can see that it diffracts, it bends that wave, and instead of having a plane wave or a linear wave, would be another term for a plane wave, okay, now we have a curved wave. We have a circular wave because it went through that boundary and bent around those openings to give us that circular wave. So that's an example of diffraction. It's a cool way to illustrate it, and we would do that in a lab normally. Now, last thing here, transverse and longitudinal. Well, not the very last thing, but almost. Okay, we are going over transverse versus longitudinal waves. Transverse waves are the waves that you typically think of. I like to give an example of a transverse wave as if you remember going back to like elementary phy ed, and you have a jump rope unit, and you've got that big long jump rope, and your friend are sitting on each side of the jump rope, and no matter how many times the phy ed teacher tells you not to touch the jump rope, you're still going to send, like, you're going to like crack that jump rope, you're going to send that wave, and it's going to travel all the way across, right? This picture kind of shows that a little bit. Okay, I moved my jump rope up and down, and it sent that wave going across. The jump rope actually moved up and down, and the energy, the wave, travels across to my partner. And that's what's happening here. We have a spring attached to this wall, and he shook it up and down. And the spring or the slinky, whatever this happened to be, moved up and down, but the energy he sent moved across. They moved in opposite directions. Okay, arrows up and down. Here, movement up and down, energy across. So transverse waves are when the oscillations are not in the direction of the wave motion. This is kind of like your typical like water wave and things like that you see more often. Okay, here's another example. Well, this is just a transverse wave in water here. And on a string, this is like my example of that jump rope, right? It's laying flat except for that part that happens to be up in the air, and that is traveling across to your partner on the other side, that even though you're not supposed to snap that jump rope, you just can't help it. Okay. Now, the different type of wave, so not all waves look like that. Some waves are different. A longitudinal wave is the other, and that is when oscillations are in the same direction of the motion. Now, that one's tougher for us to conceptualize until we see a picture like this and we get it. So here we have an area of that spring right here where you can see that spring or that slinky is compressed in one part. Okay. A lot of times these waves are called pressure waves because we have an area of high pressure here and areas of low pressure elsewhere. And that traveling area, that area of high pressure is traveling across. Notice the slinky isn't moving up and down. The movement of the slinky is in the same direction as the movement of the energy, right? So the slinky is moving back and forth like this, and the energy is also moving that direction. Okay, so that would be a longitudinal wave. Sound is an example of a longitudinal wave. So our voice creates pressure in the air, and we have areas of high pressure and low pressure that are traveling across the room until they hit someone's ears, and your ear picks up that pressure, that vibration in your ear, right? So those are longitudinal waves. Now, the last little bit is constructive and destructive interference. So what this is when waves run into other waves. Now, we would think, well, like that's not going to happen a ton, but it happens more than you think. It happens with sound all the time, right? Sound, it happens with sound all the time. So this is our example of constructive interference, which is when the waves add up to make a larger amplitude. So right here we have wave A has an amplitude here, and wave B has an amplitude here. And notice they are traveling towards one another. They are going to collide, right? When they collide, their amplitudes always add together. So we have a positive amplitude and a positive amplitude. We get an extra big amplitude. They add together, so we get a really high amplitude, right? Notice how this crest is higher than these crests are, right? Okay, we get a high amplitude. In sound, that gives us a larger volume. Okay, amplitude and volume are directly related to one another. Okay, and when the amplitude of something is increasing, the volume of that sound is increasing. So when you're turning up the volume of your car, what you're really doing is just creating a larger amplitude wavelength or wave. Okay, and then we'll notice that once they move past each other, that wave B continues to go the direction it was, but it's back to its normal amplitude. Okay, now here we have destructive interference. This is the opposite. Waves add up to make a wave with a smaller or zero amplitude. Now, same thing happens. We're still adding together our amplitudes, okay, but this time we have a positive amplitude here and a negative amplitude here. So a positive 5 and a negative 5, when they meet, they create a zero amplitude, right? So that would be destructive interference. When they're going opposite directions and they collide, their combined amplitude is less than what it was before that collision. Make sense? I think that is the last slide that I have. It sure is. Okay, well, thank you guys for listening, and you guys have a wonderful rest of your day.